Okay. So, and if you have been given the initial condition also, then you will just subtract that initial condition. Correct? So this is the time
Sir,
differentiation that we call. Yeah.
please again show 1 and 2.
So one.
1 and 2.
Okay. Okay. Okay.
Please scroll.
So it's just a simple like addition. If you have the Laplace transform for two signals, then for the summation, if you have been asked, you can directly do the summation of the Laplace transform. This can be plus minus also. There is a plus minus. And if you are multiplying some for f signal, ft signal, if you have the Laplace transform, and if some scalar multiplication has been done, then you can directly multiply the scalar multiplication. You can do the same thing in the like S transform also. Okay, S domain also the same thing. And if for a signal, if you have the Laplace transform, and for the differentiation, if you have been asked to calculate the Laplace transform, you can directly multiply the S. And if the initial condition has also been given, then you have to subtract them. Okay. And similarly, if you have been asked to calculate for the double differentiation, the same Fs minus if the initial condition has been given. So it will be something like that minus F plus zero. Okay. Yeah. Similarly, for the integration also, I told you that was like you just if so that was a dual property that you call it as. If you are differentiating in the left side in the time domain, in the S domain you just multiply S, right? Similarly, in the time integration, what happens if you have to calculate for ft, you already know the Laplace transform as fs, and if you have been asked to calculate for something ft dt, then the Laplace transform would be the Laplace transform of ft upon s. That I told you with the example of del t. You already know that for del t, you know the Laplace transform is 1, right? Similarly, if you have to calculate for ut, that will become 1 upon s. So from because unity like you can calculate in that way, right? Similarly, I gave you the example of if you have to check for the differentiation also, you can check it from the ut. Like ut for ut, you know 1 upon s, and similarly, if you have to calculate for delta t, del function or delta function, for that you already know 1 upon s times s. So that will be the Laplace transform will be 1. Okay, it's clear. And you have some more properties like time shifting, frequency shifting also. So for the time shifting, okay. So let's for example, you have been given any function for ft, you already know fs is the Laplace transform. And if you have been asked to calculate for f of t minus a, what will be the Laplace transform for this? There are some limitations, something like ROC and all, so that we are not discussing here. I'm just discussing the basic. That much we are discussing that will just help you to convert electric signal in from time domain to a S domain. Okay, that much we are discussing. We are not discussing about the ROC and all. So there's some limitation also where how to put and all. We are not discussing signals and system where there we'll be discussing the all limitations of Laplace transform and how can we go from the Fourier, well, how this is different from the Fourier transform and other things. Okay. So what about this? What will be the Laplace transform for f of t minus a?
Sir, e to the power minus a is f of s.
Correct. Yeah. This will be the Fourier transform for that. Okay. And one more thing I discussed, if we are multiplying t here in ft, then as we were doing differentiating the left in the time domain, s we are getting multiplying the s domain. Here, if I am multiplying t here, so in the in the frequency s domain, you can find the Laplace transform like this. Okay, this is what we discussed in the previous session. I guess initial value theorem and final value theorem. I'll just write it here just for the uh, like that is also been discussed, I guess, in the coming weeks. So initial value theorem, if we have to calculate for any signal that has been given, so this is called initial value theorem. This will be same as if you know the Fourier like zero. So if you know the Fourier transform, or sorry, the Laplace transform for ft, okay. So let's say example the Laplace transform is fs. If you have to calculate the value at t equals to zero, right? What can you do is the same thing you can do it. Calculate the limit for s tends to infinite. Or if you have to calculate there is a final value theorem also where you have to calculate. For example, if you want to know the value for the signal as t tends to infinite, what can you do? If you have the Fourier Laplace transform for the same signal, then from there also you can calculate just to put the s equals to 0. Okay, I guess we had done. I guess one more feature was there. I guess where if you have been given ft times e to the power minus plus s naught t, then what will be the Fourier transform?
1 upon s plus minus s naught.
Yeah, it will just be shifting, right? Plus minus times s naught, correct?
Yes, sir.
Yeah, I guess this is what we discussed in the previous session. All the addition properties, scalar multiplication, and the normal integration, differentiation, time shifting, frequency shifting, and then the initial value theorem, final value theorem. And if you are multiplying t times, then what will be the impact on the, how will you calculate the Laplace? Okay. Okay, and one more like convolution, though is not required. And the two most important thing was, and also for the delta function, you already know that the Laplace is, or yeah, Laplace is one for ut is one upon s, and for any constant, let's for example, this is k, and this is k times s, k upon s. Okay, this is how you convert from an electric circuit. And okay, yeah, for cos also you already know that for cos omega t ut, for cos s will come s square upon omega naught square, and for sine also you know omega naught of s square plus omega naught square. I hope this much we are done. Okay, one more thing, if you have to calculate for sine of omega naught t plus phi, then what will be the Fourier transform for this? Sorry, Laplace transform for this. Laplace transform. How will you calculate the Laplace transform?
So first of all, we have to uh, expand this sine omega t plus phi. There's
Yeah,
a
you can.
Sin A plus B formula by
Correct. Yeah, that. Hmm. You can use that sin A plus B wala formula. Sin A, that formula you can use it directly. Sin A, or I'll just write it for this case itself. So this will work as a constant plus cos omega t sin phi. So for this you can write it. For this also you can write it, and this will just come out as a, so cos phi s square plus omega naught square will be there for both the cases. For sin omega naught t, s generally will come from, okay, so
sir
okay
omega
for yeah, omega naught will come here, and for sin phi,
plus S sin phi.
okay,
Yes, sir. Yes.
yeah. So this is how you calculate. Let's discuss for a circuit. Okay, if you have been given the circuit, then how will you calculate? So you have been given, so this is Vn has Vi. You can just take it as 1 farad, any value, 200, 4 ohm. Okay, so this circuit you have to first convert into, use the Laplace only, and we have to calculate the V out. Okay, so you can just think of it, V in has been given, V out we have to calculate in the form terms of V input itself. Okay, initial condition is not been given, so now it's very simple, right? So if you don't have the initial condition, you can directly convert it. So how can you? So resistance will be same, right? So the resistance, if you have to write it in the Laplace or S domain, what will be this? 2 Henry. What can I write here?
2s.
2s. Okay. Similarly,
1/s.
for this 1 upon s we can write. Correct. We have to calculate the V out. Now it is very simple, right? What will be the V out? Times 1 upon s upon the total impedance. Correct. So this was pretty simple. Okay, let's. This is clear, right? Anyone has any doubt in this?
Sir, you add V in S plus 1/s or multiply?
What? What? Can you just repeat it? What did you say?
Sir, there is a multiply sign na, between 1/s and V in S.
1 by s and
Sir, you
okay.
put multiply sign or its addition sign.
Here, this one. This is multiplication, right? You just have to calculate the V out, like voltage across this impedance, right? 1 upon s.
Okay,
And then you
sir.
have to take the inverse, right? Voltage divider rule you can use, right? Here. Because you have to calculate V out, right? V out is what? The voltage across this capacitance. So this across 1 upon s impedance, you can calculate the V in term of V in, and then you can take the inverse, like Laplace inverse, to calculate the in the if you want in the term of t in the time domain, right?
Okay, sir.
Got it, right? Okay.
Sir, I won't go through the week 5 content. I have a doubt from the week 4 in the Laplace transform.
Yeah, yeah,
Can I?
yeah.
Actually, what are the conditions for the Laplace transform? Actually, for the example, if we try to use in the Laplace transformation in the e to the power t square,
A to
how
the power,
can I do this?
a to the power,
What are the conditions? E to the power t, e to the power t square.
t square. No, like I'm not getting what you want to do from this. E to the power t square.
I just want to know what are the conditions where can I apply the Laplace transformation? For example, if we try to the try to evaluate the Laplace of the e to the power t square, Actually, I can't do that. I can't able to solve this, and I Google, try to Google it. It shows the Laplace will not be valid here.
For e to the power t square.
E to the power
See,
t square.
e to the power t square. Right. Okay. See, there are, that is what I said in the starting. There are some limitation for the Laplace transform that will be seen when you'll be knowing about the ROCs. Like, see, Fourier transform you can calculate for any signal, but Laplace you can't calculate for every signal. Like, this is just, if you're just thinking this as a signal, you can't calculate for every signal the Laplace transform for that. Okay, there are some limitation that we care about. Like, uh, we check, like even for a simple signal like e to the power minus 80. Okay, if depends upon the time, like if the time domain, if you're just taking as ut, then you'll be able to calculate it. Okay, and if you are taking some other time domain, right, then you'll not be able to calculate for those cases. Also for the simple signals also you'll not be able to calculate the Laplace. Okay, so that's why, so whatever signal that we are dealing, for those all signal that we have calculated, there are some ROCs for that. Are you getting me?
Okay.
Yeah,
That was my question. What are the
yeah.
limitations?
So that, okay, see, let's for example, if you have to calculate for e to the power minus 2t, see, how do you calculate the Laplace transform? You calculate the Laplace, whatever the function that has been given to you, to the power e to the power minus st, and then you integrate it, correct? See, whenever the
Yeah.
integration, you just have to, you will be able to calculate the Laplace for those signals only, where the integration that you are getting will be converging toward some fixed value. If the if integration is not converging towards some fixed value, okay, for those cases the ROC is not defined, and then you call it as, you can't calculate the Laplace transform for those cases. Okay, but that doesn't come under when you calculate for the Fourier transform for any signal. Okay.
Oh,
See, these are ROCs are like, you just check for those signals where you are able to find, like for ROCs, let's for example, for a greater than some, like x greater than some a. For those cases, the set of complex number for which the signals will converge, the Laplace transform for this, the if you will integrate it, basically the value will start convert, like will get some fixed value. For those signals, you'll be able to calculate the Laplace, but for the other cases, you'll not be able to. That we don't have to go through now, but these are the limitation, uh, based on the ROC. Okay, the region of convergence, where the Laplace, this signals, the region of convergence is defined. If the region of convergence is defined for this signal, then you will be able to calculate the Laplace. Otherwise, will not be. It's not defined itself, the Laplace for many signals. Just a very limited signal you'll be able to calculate, where you'll be able to find the region of convergence, where the integration that you are doing, it will be converging, okay, towards some fixed value. Otherwise, you'll not be able to. Okay, let's for example, e to the power minus 80. E to the power 80 signal itself you take, whenever you'll do, like let's just put it here, e to the power 80 minus st, right? So that means what? The signal will be a minus s, correct? If the a minus s is greater than 0, for those cases you'll not be able to, because the integration will not be coming out to be some limited value. But a minus s is less than 0, for those cases you'll be able to calculate the Laplace, right? For a minus s greater than 0, this will be what? E to the power some positive value, and then the integration will be not like, it will not be finite. So for those cases, for this type of signals where e to the power 80 is just been given and a minus s is greater than 0, they, okay, so for these cases you'll not be able to calculate the like Laplace transform. But if a minus s is less than 0, then you'll be able to, because for those cases this will be e to the power some negative value, and then you can do the integration, right, from 0 to infinite if you are taking, like ut is multiplied then. Okay, is it making sense?
okay, sir.
Yeah.
We are going to discuss about the ROCA and all
And the
after.
signals, no, signals and system we'll be discussing. Here we are just taking the help of Laplace, like to convert any like electric circuit. It is just helping us to convert. And whatever we have, like we just have, we generally use what? The voltage source is some constant or some variable, maybe in the sinusoidal. So for those cases, it's pretty simple to calculate the Laplace. So that's why we are using it here. In the we are going to some different domain. In the S domain, we are converting, calculating, and then coming out again in the time domain. So here, whatever the signal that we are taking, we generally take the impulse. Like at t equals to 0, we just give some voltage or some current or something. So that is simple form of a impulse we are giving. So for the impulse or for a single step functions, we have the Laplace. Like Laplace has been defined for those cases. So we don't have to worry about those. But in signal and system, we'll be learning more about like for which signals you'll be able to calculate the Laplace and for which signals you'll not be able to. Okay.
Oh, okay.
Yeah. Okay. So
Sir, please complete the previous problem.
okay. Yeah. So this question I was asking about how will I calculate the V out? So if you have to calculate first for this electric signal, the circuit that has been given, we'll be trying to convert that in S domain. We have written in S domain, so voltage, the resistance will be same. The inductor will be like like L time S, right? And then the capacitor will be 1 upon Cs. So this will be the whole in the S domain. Now I want to write the V out in the term of V in. Okay, how can I write? So V out is what? V out is simply what? The voltage source we are applying some V in here, correct? So this V in is getting divided between 1 upon S and 2 upon S, 2S, right?
Yes, sir.
So you can use the voltage divider rule here. So it will be what? 2S time plus 1 upon S.
Then, sir,
Okay.
if we have if V in is known, then we have to calculate. We can find the V out.
Yeah, we can calculate.
If
If we have been asked to calculate the transfer function like V out by V in itself, V out by V in, then you can write it
okay,
as 1 upon S times 2S plus 1 upon S. Okay, that will be like, we can simplify this.
okay, sir.
Okay.
Okay, sir.
Yeah. So, and then if we have been asked to calculate in the form of like time domain, then we have to take the Laplace inverse of that. So let's do it for this case at least. V out for the transfer function itself, that will be what? 1 upon S times 2S plus 1 upon S. That will be what? 1 upon S. That will be, S will get cancelled and you will be left with 2S square plus 1. Right? So this will be 1 upon 1 plus 2S square. Okay, this is what? V out by V in. And now if I have to take the Laplace inverse, how can I take the Laplace inverse of this case? 1 upon 1 plus 2 square.
Taken 1 by 2 as a common.
Okay, what? 1 by, we can take it as 1 upon what? If we just divide it, just divide everything by 2, you'll be left with 1 upon 2, 1 upon 2, and then S square. Correct? So I'm just trying to write it in the form of, we can use this property, not property, like either this one cos omega naught t or sin omega naught t. If you have been given like this, right, this is what will happen if you are just dividing with 2 everywhere. So this will be left with, and now this is what, so we can write it in the form of sine. What will be the value of omega? This you can write
Root.
it as 1 by root 2 whole square. Correct?
Yes, sir.
Yes, sir.
So 1 by root 2.
T.
Correct? We'll be getting the same, right?
And 1 upon root 2 as a multiplication.
1 by 2.
Yeah. 1
One.
by root 2 times 1 by root 2. So you'll be having 1 by root 2. Correct. Is it clear? This one? If you have to calculate the Laplace inverse of 1 upon 1 plus 2s square, what can we do? We can just think of as we have to go like it can be a Laplace transform of sine or maybe cos. But after that,
Your screen has been fixed. Are you writing something?
is it? You're not
It's
able
visible
to
to us, sir.
see the screen. Oh, okay, okay, sorry. Okay, I'll just. Is it visible now, everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. So if I have to calculate the Laplace inverse of 1 upon 1 plus 2s square, you can just think of as this is some form of omega upon s square plus omega square, and that is the Laplace transform of sine omega t. So what we have done, we have just like because s square was not having any scalar multiplication, so we have just divided with 2. So we are left with 1 upon 2 upon 1 upon 2 plus s square, and then we have found that out that this is the the Laplace inverse of 1 upon root 2 sine of 1 upon root 2 t. Okay, yeah, this simple, right? This was pretty simple. Anybody has any doubt in this? No, right? Okay. You guys can hear me, right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Similarly, so this was very simple. If you have to ask to calculate any simple signal like circuit has been given, right? Let's for example, you have been given some form of 3 ut and calculate the I. So this also is very simple. You just write it in the form of uh, like this is also very simple. You just write it as 3 upon s, and for this you will write it as 2s, and this is same. And then you can use the KVL to calculate the, and you just write it in the form of the S domain, and then you take the inverse. You'll be getting in the time domain. Okay. Now, if you have been given, and okay, so this is simple, right? No doubt in this. This was much easier. So now let's try a difficult problem. So let's try this itself.
Sir,
Yeah.
in previous one, after Laplace transformers circuit,
In this question or the last one? This one? This question, right?
after Laplace transformation circuit, after
Uh,
yes sir. Next, current will be Is in the circuit.
yeah, current will be I.
Second one,
Yeah. So we can calculate it like IS will be what? IS, right?
yes sir.
Yeah. And then this is much easier to calculate the inverse also. So you can calculate the inverse also. Now I'm giving this question where you have been given the voltage. Okay, so we have to calculate the value of I1t and I2t. Okay, so what we'll be doing, we first have to write it in the form of in the form we have to go from time domain to S domain first. So there is no capacitor, only the inductor. So two inductor are there. I will just write it here itself. So here it will be what? 10 upon S. This will be 1 only. This will be 0.25 S. This is 4 only. And this is S. Correct? Now, KVL in the. So, can somebody tell me the equations? If I just have to go like this.
Yes, sir.
Yeah. What will be the equation? The
10
KVL
upon
equations.
S. 10 upon S.
Okay. So, how you are taking potential? Okay, we are taking, okay, 10 upon S, or maybe take 10 upon S
Minus I of S into, sorry,
minus 9, huh?
1. 1 is there, so minus I of S.
Yeah. Or maybe take it like this. You just go it from, we are going from minus, so minus 10 upon S plus I1 time 1. This is I1S and this is I2S. Okay, so if you are taking I1S minus I2S times 0.25S equals to 0. Correct? This is the first equation. Right? Anybody has any doubt on this? The second equation. Okay, now tell me the second equation. How will you write the second equation? This is the first equation. Use the KVL in the second loop.
Yeah.
I2S
I2
minus
minus
I1S.
I1 0.25 S. I2 minus I1 0.25 S.
Okay, I2 minus I1S times 0.25
S plus 4 I2S
plus 4 I2S.
plus 1 SI2.
Okay, now how will I solve this? How can you solve this? It's very lengthy, right? Anyone is getting any idea? How will you solve this? This is very lengthy, I guess. You have to take
No,
out.
sir. Subtract, subtract first from second. So we get cancel out the terms. No add add first and second. Cancel out the term I2s minus I1 and 1s minus I2 0.5s 0.25, sorry.
Correct. So if you just add this two equation, 1 plus 2 itself, this will get cancelled out, right?
Yes, sir.
You'll get something in the form of I1, I2. From there, okay, so you can just write it as I2, I1 is minus 10 upon s plus 4 times I2 plus equal to 0. So I1 is, you can just write it as 10 upon s. So this I1 we have to put in some of the equation. This is going to be crazy, I guess. Yeah. Any other method that you can think of to calculate? I don't think so. There's any other method that'll be simpler. It'll be a bit calculative only. No other method to solve this.
Sir, KCL?
Even KCL, where will like
This is the simpler one to solve the equations.
where
Mm, we should put I1 anyway.
no, there's only one method you have to take out. You have to take the value of, yeah, whatever the value that we have got I1. You have to put in one of the equation, and then only you can get the I2. Like put the I1 so that the whole equation will be in the form of I2 itself, and then can calculate the I2. The equation that we wrote was correct, right? I guess that is correct. No problem in that.
Also,
Okay.
sir, if we find V at node, then we can get I1 as V1 minus 10 by S. I1 as.
Where at this point, huh?
Yes, sir. So we can get V minus 10 by S divide by 1, then I1.
Hmm. Okay, let's try it out. Okay, first let's try. If you just write the value of I1 in the first equation, which one is simpler? Both are, yeah. Okay, this you can do it at home. I am not. This is like I thought it will be simpler so that we can directly calculate the Laplace and then Laplace inverse, like the Laplace inverse for that. But this is going to be a lot of calculations. So, okay, let's try it out. This is what. If I'll just write it I2 here, this will get cancelled out, right? So this will get cancelled. So we'll be left with I2 4 plus S plus I1 minus I2. Okay, leave that. You can do it. I guess this was some of the your one of your practice assignment questions only, so you can try it out. But the equation that we wrote is correct. Only you have to do the like you have to write this I1 in one of the two equation and then solve it. Or maybe that matrix method also you can use it. But again, yeah, that also you can use it. That will also be a lot of calculation. Okay, leave this question. Let's try some other question then. This only the calculation part. I don't think so. There is any conceptual uh, thing is there that will trouble you. Other than that, only calculation is there, right?
Yes, sir, we can do it.
Yeah. Okay. So, any doubt that you have from the previous weeks, from week 4, anything that you have faced? Any doubt that you have faced from week 4? I guess week 4 you have submitted also the graded assignment, right?
Yeah. Yes, sir, but I have a doubt in a delta function.
Yeah, what is the doubt?
How we get Laplace transform for a delta function? Is it experimentally given that a delta function has a Laplace transform 1?
See, delta function is what? What is the delta function? How do you write mathematically the delta function?
This is a function y and x
No, delta function at t equals to 0, what is the value of the delta function?
tends to infinity, I think.
Yeah, this is infinity. And for all other value, it is 0, right? So this is defined as like this. This is infinite. But normally, whenever you see, it will be shown like this, right? The value is 1.0. So what happens? See, this generally comes out from, you can just think of as a rect function, a rectangular function, right? Okay. So there is some width. Let's for example, the width is t. Okay, and the height is 1 upon t, so that the area is 1. So when you will start decreasing the width, okay, so when the t will start tending towards 0, so the height will be 1 upon 0, it will start tending toward infinite. So the area that will come under a delta function 1, that you already aware of that, right? So the area under a delta function equals to 1. So whenever a delta function is represented, right? So this is the one value that has been represented here is not the magnitude, but the area. Okay.
Okay, sir.
So the
Now I
magnitude, you got it right. Okay. So this is not like the magnitude, just the area. So if you will calculate the Laplace, you'll get 1. Laplace transform will be 1 for a delta function. Okay. Any other doubt anybody has? Till
Sir,
week
I
4,
have a
any
doubt in week 4 graded assignment question 7.
week 4 grade assignment question 7. Okay. Let me open it. What is the doubt here?
Sir, I solved this question but I get wrong answer. I don't know where I put mistake.
Okay, so graded assignment for question number 7, right?
Yes, sir.
So the question is, if t has been defined as t minus 1 for t 1 to 2, t from 2 to 3 is taken as 3 minus t and 0 otherwise. Okay, you have to calculate the Laplace transform with this, correct?
Yes, sir.
So how did you calculate that?
Sir, I calculated into a piecewise function like
Hmm,
from 0 to 1 f of t is 0, from 1 to 2 is t minus 1, and 2 to
right,
3 is 3 minus t, and 3 to infinity is 0.
okay. And from 2 to 3, this is 3 minus t, time e to the power minus st dt. Yeah, this is what we have to calculate, right?
Yes, sir.
So we'll be having problem. This will trouble t times e to the power minus st 1 to 2. Other than that, the other part will be simple e to the power minus st integration 1 to 2 dt. This is simple. Even this is simple. Plus 3 times e to the power minus st 2 to 3 plus minus sorry t e to the power minus st 2 to 3 dt dt. So this two term, I don't think so any problem, uh, any major problem will occur for this two equation, right? For this and this, right? So this is in the form, okay. So we'll be having some three term, right? Even, okay, let's try to guess the answer. Yeah, okay, so let's try it out for this first. This two part you'll be able to do it, right? Only this is the other part. So t times e to the power minus st for any 1 to 2, and the other part is minus t 2 to 3 e to the power minus st dt. So here you have to use the UV wala equation, right? Correct. Here also there is no conceptual as I see. Anything else we can do? Any properties we can do? Use. Okay. See,
Using by parts.
by parts we can use. That is, I am asking. Can we use any properties that we have discussed till now?
But sir, these properties are for limit 0 to
No. Yeah. Correct. Correct. We can't use it because even though you can't use it for any cases. Even for this cases also you can't use. You have to do the integration.
yes sir, we have.
So you can't do anything here. So for these two cases, okay, fine. But here, uh, for this case, we'll have to use this. I guess there is only calculation, no as such. But so you can do it. Like, how do you do u times v? How do you do that? You take the u times and then you integrate the second, correct?
Sir, have integrated direct
Can you do
t
direct?
minus
No.
direct. Yeah, yeah.
How?
U into t minus one, then integration following uv
Huh,
rule.
huh. Yeah, yeah. That only we can do. Yeah, correct. So apart from that, we can't do anything. So du by dt times v. Anything else we can't do. Only this method only we can do. So for these two cases, it's fine. E to the power minus st upon s and put the value of 1, 2. Similarly, for this case also e to the power minus st upon s. That is fine. But for these two cases, you have to use like uh, multiplication of this UV rule you have to use. So apart from this, I can't see any other method to solve this question. Right?
Sir, we can't use that method which was told by Professor Bobby in a lecture, that he put the same question t e की power minus st with limit 0 minus to infinity. So he said it is a derivative of minus d by ds of e की power minus st. So he put that in equation and he solved from 0 minus to infinity. So I also did the same method, but we changed the limit like 2 to 3 and 1 to 2.
Okay, you are saying this method. Huh?
Yes, sir.
I guess this is what you're trying to say. Whenever you differentiated this one, uh, this one you're saying, or let's for example, you're saying this one you're saying, right? This one you're talking about. Can you hear me?
No. Sir,
This
yes,
one you're
yes,
talking
sir.
about?
Yes, sir. Yes, sir.
No, this is like if you have the like it depends on the limit, right? So if you have the limit from zero to infinite, then you can, or maybe minus infinite to infinite, then you can use it. Other than
So
that, you
we
can't use this.
use this like when we have limit 0 to infinite only.
Yeah, yeah. This all property will just be using when your limit is from zero to infinite. If you are dealing about unilateral, like, and if you are, if even if you are from minus infinite to infinite, you can use it, but not for this case because here specifically they have mentioned the limit. Okay, 0 to 1. But this type of problem mostly will not be asked anywhere. So this is just for the practice. Otherwise, nobody is going to ask you like to calculate the Laplace between 1 to 2 or 3 or 4, something like that. Okay. So,
So, sir,
okay,
we can
even the,
solve this like integration by part.
yeah, yeah, only that is the only solution to solve it. So from the basic approach only, you can solve this all questions. This integration by parts only, you can use it. Other than that, there is no other rule. You can't use the properties because the limit has been given here.
So we can use that, but limits will be changed according to S, I think.
No, you can't use the like you. How will you use this? This method you can't use, right? T times because whatever has been defined, you can't use that, right? Because that has been done for some different limit from 0 to infinite or from minus infinite to infinite. Okay,
No, sir.
even for
I
what?
am
Yeah.
talking about if t e की power minus st is given to us.
Hmm.
So if we are going to differentiate it with respect to s, then we can get uh, t e s. I think I should calculate.
No, if you have the limit has been fixed, then I don't think so. You'll be able to use any of the properties.
No, sir, I am not talking about the properties. These are all
Then,
given by the limit 0 to infinity. I am talking about the procedure.
procedure. See, even though whatever the properties that we are talking about, all those has came from the basic method only, where you are integrating every function with multiplying first with e to the power minus st and then integrating. Correct? That is what the Laplace transform is. So here also, if you have been asked to calculate the Laplace transform, you have to multiply that signal, given signal with e to the power minus st, and then only integrate it to calculate the Laplace transform. So we have calculated, right? In the last session, we have calculated for some of the signals like the exponential decaying signal, or maybe for ut, the unit step function or the delta function. We have calculated the Laplace transform, right? Those are only you can calculate it like this is the basic method, right? To calculate for the Laplace transform for any method, you have to do from minus infinite to infinite or from wherever the signal is defined from ft e to the power minus st dt. Okay, and if you have to get the signal back, then you do it like this. This to get the signal back, like Laplace inverse that you call, and this is the Laplace that you calculate. Okay, so for this, if you have been asked for this signal, you have to multiply e to the power minus st, and then only there is no other method to calculate this. Okay,
Sir, I am talking about that. First of all, you have to scroll up
yeah,
at the at the integration of e t minus s dt. So
integration of t.
of
Okay,
t
t.
to the
Hmm.
power e into s. Okay, okay. So we can write it as a
This you can
difference.
use it like in
Sir,
integration. Yeah, by parts you can use it.
yes, sir. By parts we can solve it, but another method
Huh.
we I am just suppose uh, that we can differentiate e to the power minus st with respect to the s. But the rare condition, which is the problem which occur, is about the limits. The limits are given with respect to the t. We should interchange these limit with respect to the s. Then we can calculate by the that matter method. Sorry, which is raised by the Bhavana Kumari, I think. Only the thing is about the limit. Limit is given to the in the respect of t, but we have to uh, give the limit in the form of s if we are going to use that method.
Uh,
Are you getting
Yes,
it?
okay.
is this possible?
I don't think so, but if somebody's saying I can check it, but I don't think so. And how will you change the limit? The problem here is if you are going from time domain to the some S domain, how will you change the limit? That is also a question, right? You can't change the limit. Like, how will you change it? You, if there is some relation has been given, then only see I can understand what you are trying to say to go from one to like you change the variable. But here it's not about changing the variable. Like you can go from T to S, but how will you change the limit? Like let's for example for T equals to some value, what was the value for S that you don't know, right? Then you can't change the variable also. Uh,
Yeah.
Yeah. So that's why you can't use this method. It's basic. First of all, this type of questions nobody will be asking you. Okay, this is for the graded, just for the practice, even for the quiz also, because only the standard signals generally is asked. Okay, and for the standard signal, normally because in any of the circuit also always you'll be having the some standard signal only, not any random signals like this. This is just to check like whether from the basic approach you are able to either the definition of Laplace or not. That is when nothing else for this question, because like some a lot of calculation even in the exam it has been asked like most of like even I can do like there because just integration by parts, and that will take a lot of effort, and then in the end you'll do some calculation mistake and you'll do some error. So yeah, but only the standard method. Just if you know the properties and basic thing about the Laplace, I hope that is more than enough for anyone. Okay, this just an okay. You have done some mistake, that is fine. But with the basic approach, you will solve it. Like you just have to multiply e to the power minus st and integrate it. Use the integration by parts, and then only there is no other method. That's it. There can be, but I am not aware of anything else. Okay. Anything other? Any other doubt? Anybody has? So we'll have to start from the transient. Like we have to take now. We'll be solving all the questions where we'll be having the initial conditions, final conditions, all those things, right? Okay. Only those concepts are left. I guess week 5 mostly in those type of questions only has been discussed. So Laplace now you are aware of that, how to calculate for some standard signal now, and even you know how to change it from a capacitor. If you have been given the electric circuit, how will you change it in the S domain? Now only the remaining conditions are, I guess, for this whole 4 5 weeks was all Laplace, and in the end, you just have to know some of the transient condition when T zero condition, zero plus or zero minus conditions for the capacitor and for the inductor. Only those type of questions are left, and that we have some 2 sessions again. We'll be discussing those things for the week 5, and then we'll be done. And the coming next week, we'll be just be solving from week 1 to 4 questions for the quiz 1. Okay. Any other doubt anybody has till now, whatever we have discussed or whatever you have till whatever you have submitted till week 4? No, right?
No, sir.
Okay. See, for this, because see, there are a lot of concept has been mixed and has been put in one course, right? So it's like a network theory, and then you will be going through BJT also, and then MOSFET, also two-port network also. So many of the concepts are there. So only one thing, we can just try to solve as many as questions just to have a more clarity on your like more conceptual clarity. So this course is important for the upcoming whatever the course that we'll be taking like analog, or even we have been discussed a lot of things like Laplace has been discussed that we'll be covering in much more broader aspect in the signals. Again, the BJT will be discussed here. Like, and again, the whole course, the analog will be just discussing regarding, we'll be moving about the BJT or the op-amp only, right? So here it's just the 1 or 2 weeks. Again, the MOSFET has been just discussed in 1 or 2 weeks. There will be one, the whole course itself on the MOSFET itself, the VLSI ability. So here you just are getting the basic idea, the basic concept, but again, in the coming diploma, you'll be having in one topic itself, you'll be having one whole course itself. Okay. So just try to practice as many questions as possible. Try to solve at least the gradient in practice, and whatever the question that this is like basically I'm taking like whatever the question that we are discussing that you should be knowing, and that is more than enough. Okay, so we'll be meeting again day after tomorrow, I guess, in the Saturday, and
Sir,
we'll try to yeah.
sir, can you recommend any book for this? I don't have a practice.
I have some questions. I don't recommend any. I don't recommend.
Okay,
I
okay.
don't have any book, but I have some question that I can share to solve. As of now, I have to leave. I'll just close it out the session. Okay, I have to leave for the.
Okay.
I have some other meeting. Okay, thanks everyone, and have a good day. Bye bye.
Okay,
I'll
thank you.
share
Thank you,
the
sir.
question. Yeah, I'll share the questions where you can practice it out. Okay. Mhm.